SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 46 of the Statistical Thermodynamic course. Now, as you can see over here, so the non-resonant, so if we see these expressions that we wrote, okay, of A1 naught and A naught dot. So if we look at these, it is now seen that the non-resonant higher, if we say, let us neglect the non-resonant higher frequency terms. Okay. So as their effects essentially average to 0 because they are rapidly oscillating functions of time. So we define delta omega 10. So therefore, the equations for A naught dot, that is the variation of A naught, omega r A1 to A1 dot is equal to I minus I to A naught. So these two equations that you see over here, okay, they can be actually solved analytically. The difference delta is often called, this is called the detuning frequency. Okay, since it measures how far the electromagnetic radiation of angular frequency omega is tuned away from the resonant frequency. Because this tells us that how much the electromagnetic radiation, EM radiation of frequency omega, okay, is tuned away from the resonant frequency. The resonant frequency omega 10. Okay, so this is called the detuning frequency. And you also realize that why the non-resonant higher frequency terms can be neglected, because they essentially average out to 0 because of their, fast, because they are very rapid in nature. Okay? So now that we know the solution to these two first order simultaneous equations, these are two first order differential equations with initial conditions are okay, A0 at 0 is equal to 1 and A1 at 0 is equal to 0. For the system, okay, initially in the ground state, all right, equal to 0, all right. So therefore now A naught T will solve to cos let me write it down and then we will go term by term. By 2 and A1 T omega T 2 omega T by 2, in which where omega to omega r square plus delta square half. Okay? That is what your omega is. So this solution, if you just substitute, you will see that they actually agree with the equations that we are talking about. So the time-dependent probability that the system will be found in the excited stage, so the time-dependent probability that the system will be found in the excited state is given by is equal to omega square sine square. So that this is the time dependent probability that a system will be found in the excited state. Be found in the excited state, where the corresponding time dependent probability that the system will be found in the ground state, corresponding time dependent probability that system will be in ground state is given as one minus a1 square is equal to 1 minus omega r square sine square. Okay, so at resonance, okay, delta detuning frequency is equal to 0. This is equal to omega r. Okay, so in that case, your a1 square becomes sine square omega rt by 2, and a naught square, okay, becomes 1 minus sine square omega rt by 2 is also equal to cos square omega rt by 2. Okay, so this transition probability, now the transition probability a1 square can be now plotted for three different detuning frequencies. So let us draw that. Okay, so this axis now has a1 r, and this is t divided by 2 pi omega r. Okay, and this is 0 0.5 1 5 2. Okay. Okay, so when the detuning frequency is 0, we'll curve like this. Okay. This is a detuning frequency 0. Okay, then let's take detuning frequency equal to the Rabi frequency. Okay, so that will be given as it's a little bit like this. Okay. And so on and so forth. So this is drawn for delta is equal to omega r. And then if you go to the detuning, even smaller detuning frequency, so this is with delta equal to 3 omega. Okay, so this is the plotting. So the meaning of the Rabi frequency now becomes clear if you look at these two equations. So if we look at this equation, which was E by H bar, and if you look at the equation which is A1 bar square is equal to sine square omega r t by 2. Okay. Okay, so the Rabi frequency is being clear from this. The system is coherently cycled. Coherently cycled, that is with no abrupt changes in the phases of the amplitude of the wave functions between the ground state and the excited state by an electromagnetic radiation. At resonance, the system is completely inverted after a time of pi by pi r. So if you look at it, this is basically your 1. So at the resonant frequency, the system is inverted. You can see it is inverted completely at the resonant condition. So it's completely inverted between the ground and the excited state. And this inversion happens after a time which is given as T pi, which is a pi by omega r. Okay, off resonance, while at off resonance, there is a reduced probability of finding the system in an excited state, which is also shown in this particular figure. That these are at detuning cases when the incident radiation is detuned by that particular amount, you will find that the system will have a reduced probability to begin with. The system will have a reduced probability to begin with, and that is exactly what happens over here. This probability is reduced. If you further detune it, it is the probability of the system existing in that particular excited stage. This is about 0.5. You can imagine how low this is. Okay, so we've got two things. At resonance, the system is completely inverted after a specific time scale. We also understood the meaning of the Rabi frequency. If you look at these two terms over here, these two expressions, and off resonance, there is a reduced probability because of the detuning nature. So this is a picture of a coherently driven system that has ignored all decay processes, such as spontaneous emission from the excited stage. So the spontaneous emission of a photon will bring the coherence of the emission, coherence of the excitation, and reset the system to the ground state. Similarly, collisions, okay, collisions can also cause relaxation in the system. In fact, collisions can reset the phase of the wave functions, okay, without changing any of the population. So these phase-changing collisions also interrupt the coherent cycling of the system. Okay? So all these things are actually present. Okay? So if you have a system now, if you consider a system in which there is a relaxation process going on, let's draw this. This is time, and this is once again A1 prime. So that is the probability. So undamped system will have very nice. Okay, so this is 1. Okay, moment you start have damping. Okay, this will start to decay. And so on and so forth. So at the relaxation processes, so these are the damped systems because of relaxation. Okay, so so the effect of, for example, collisions and other relaxation phenomena is to damp out coherent cycling of the system. The system, also called the Rabi oscillation. Oscillations. However, the Rabi oscillations can be observed in any quantum system by just increasing the intensity of the radiation. This increases the applied electric field. So at some point, the Rabi cycling frequency exceeds the relaxation frequency, and the coherent behavior will be observed. Okay. So if omega r is much greater than omega relaxation. Okay, a coherent behavior, okay, or which is called the Rabi cycling, will be observed. Sometimes you do it by increasing the radiation intensity. Increasing the radiation intensity. Okay, now there are NMR and other processes which can actually do that. Okay, so we can see that how collision processes and even like stimulated or rather spontaneous emission can also, you know, break this coherent cycle. They break the coherent cycle. Okay, coherent cycle of the system. Okay, so that is good. So now that we know that what it is, so we can now then, you know, got an idea, fairly good idea of what. So next we are going to do something called, which is very relevant to absorption spectroscopy. Okay, so that will be called the Beer's law. So let's take a look at something that we are going to do next. Is Beer's law. Okay, so consider a system like this. Draw it first. Okay, so this is like a 1 meter by 1 meter. Okay, and there are two energy levels, say 1 and 1 and there is radiation which is coming at this. Okay, so this is a system where there are n0 molecules. Is n0, not no molecules, n0 molecules per cubic meter in a ground state, and n1 molecules in excited stage. Okay, so there is a flux of photons, okay, which is given as F0 is equal to I0 by H. Okay, is incident on this left face of the cube. So if you consider this to be the left face of the cube, this is the left face of the cube where there is an incident photon, which is in the unit of meter square second inverse. Okay, which is incident upon the left face. So all these photons, what they will do, they will travel through the system and they can be absorbed or they can induce stimulated emission. So what is the intensity of the radiation after a distance, say L? Okay, after a distance L. And this is a differential section, which is dx. Okay, so this is a distance L of the box. Okay, so there is a flux of photons. These photons can either be absorbed or they can trigger stimulated emission. So what is the intensity after a certain length L in this particular box? Okay. So let us do that. dN1 by dt is equal to minus d1 to 0 rho n1 plus d 0 to 1 rho n0. We'll see what rho is. Rho is basically I by C is equal to H FC by C. Okay. Now coming from this expression after this, what will happen? dN1 by dt is equal to 2 pi square mu 1 naught square p mu naught h square. We will see how to get to this actual expression. Okay, so that will be a part of a tutorial. G v minus v naught rho. Now you may be thinking that what this G is and what this other things are. So we will take a detour right here. Okay, after this is done, after this expressions are done. So this is mu 1 naught square v by v naught epsilon naught hc n naught minus n1 g v10 into f. This gives rise to dN1 by dt is equal to sigma f n naught minus n1, okay, where sigma is equal to 2 pi square mu 1 square divided by 3 epsilon naught hc g v minus v1. Okay. This has got a dimension of meter square. Okay, the physical interpretation of sigma is as an effective area that the molecule presents to the stream of photons of flux F. So this is basically the effective area that a molecule presents to a flux of photons. Okay. Now, of course, here you notice a few things like G and how did I get these expressions that you see over here. For that, we need to take a little bit of a detour and try to understand that what happens, once radiation interacts with matter. Right. Now, in order to do that, okay, let us now take it case by case basis and try to get a reasonable idea that how the buildup of the population in an excited state happens and how relaxation is actually important in taking away these transitions, breaking the coherency of these transitions, and how they lead to what we call something called a line-shaped function. Okay, so for that we need to take a little bit of a detour, okay, and try to find out that how these absorption coefficients can be evaluated from the first principles. So for that so here is a case for a small detour. Okay, so if you recall that the magnitude of force of attraction between two electric charges, force of attraction between two electric charges are given as F Q1 Q2 divided by 4 pi epsilon r square, right? Okay, so there is of course a half term, but we are not going to go over there. Since a typical electronic transition has a lifetime of about 10 nanoseconds, the effect of Rabi cycling are already present at 1 watt. Okay. At megawatt or higher power levels of pulsed lasers, for example, what we get, the coherent effect of strong radiations are even more pronounced, provided electrical breakdown is avoided. At these high electric field strengths, however, the simple two-level model is not a good description of a molecular system. Okay, so that is the prelude. Okay, so you understand that a typical electronic transition lifetime is about 10 nanoseconds. So the effect of Rabi cycling is present, which is a coherent cycling. So at higher pulse levels, higher power levels, we can see that the Rabi cycling can be even more pronounced. It is pronounced even at 1 watt. Okay. So there is also much confusion about the various terms and symbols in the field of radiometry. Intensity of a laser beam can be called irradiance in radiometry. In radiometry, intensity and spectral intensity are used for power per steradian and power per steradian per hertz respectively. So there are all kinds of nomenclature issues as well. Okay, so these are the things that are there. However, the spectral radiance of a black body, is given as rho Vc by 4 pi, which is equal to 2h cube by c square into 1 by h mu by kt minus 1. So the case of weak electromagnetic radiation interacting with the system is also common. In fact, before the development of lasers in the 1960s, weak field case applied to all regions of the spectrum except the radio frequency and the microwave region, for which powerful coherent sources were available. Okay, in the weak field case, there is a negligible buildup of population in the excited stage. So for weak field non-laser, okay, A1 is almost equal to 0 and A0 is almost equal to 1. As a result of that, A1 dot is I omega r by 2 E minus I delta t. Okay, so this can be readily integrated, okay, to get A1 I omega r by 2 0 to t E minus I delta t dt. So A1 is omega r by 2 delta E I minus delta t minus 1. So probability of finding the system in the excited stage after a time t is then obtained from this particular equation that we have written over here. Okay, so E1 0 to 1, that is the probability, is A1 square, therefore given as omega r square delta square sine square delta t by 2, okay, is equal to mu1 naught square e square h bar square sine square omega minus omega 1 naught t by 2 divided by omega minus omega 1 square. So this formula is deceptive because it assumes monochromatic radiation and short interaction times. These requirements are inconsistent with one another because of Heisenberg's uncertainty principle. So in the next class, we will see that how some of these things actually unfolds. Okay, but this is the probability of finding something in the excited stage for a weak field of radiation.